Welcome to our lecture on ordinary differential equations. Today, we are going to explore the fascinating predator-prey model, a mathematical story of survival, balance, and the endless cycles of nature. Whether you are looking at foxes and rabbits in a forest or complex chemical reactions in a lab, understanding how two interacting systems drive each other's growth and decline is one of the most powerful tools in applied mathematics. Let us dive in and see how we can translate nature into numbers. To understand this model, imagine an isolated island, inhabited only by rabbits and foxes. The rabbits have endless grass, so their population wants to grow rapidly. But the foxes rely entirely on the rabbits for food. When rabbits are plentiful, foxes feast and multiply. However, as the fox population explodes, they eat too many rabbits, causing the rabbit population to crash. With less food, the foxes begin to starve, allowing the rabbits to recover. This creates a continuous, never-ending cycle of boom and bust. Now that we understand the basic story, let us look at how we translate this into mathematics using the Lotka-Volterra equations. To keep the math manageable, we make three strict assumptions. First, the prey has an unlimited food supply and grows exponentially without predators. Second, predators will starve at a constant rate if there are no prey. Third, the rate at which predators eat prey depends directly on how often they bump into each other, which is proportional to the product of their populations. These assumptions lead us directly to our first differential equation, which tracks the prey. The formula comes from taking the natural growth of the prey and subtracting the number of prey eaten by predators. In this equation, dx by dt is the rate of change of the prey. Alpha is their natural growth rate. If alpha increases, rabbits reproduce faster. Beta is the predation rate, representing how deadly an encounter is. Finally, y is the number of predators. As y increases, the subtraction term grows, slowing down the prey's growth. Having modeled the prey, we now apply the same logic to the predators. Their equation is built by taking the growth from eating prey and subtracting their natural starvation rate. Here, dy by dt is the predator's rate of change. Gamma is their natural death rate when they have no food. If gamma is high, they starve quickly. Delta represents their reproduction efficiency, meaning how well they turn a hunted rabbit into a new baby fox. Notice that the growth term depends on both x and y bumping into each other. Before we move on, let us see this with a concrete example. Suppose we want to find the equilibrium points of a park, which are states where neither population is changing. We are given specific values for our growth and death rates. To find these balance points, we must set both differential equations to exactly zero. We start by substituting our numbers into the prey equation and setting it to 0. By factoring out the common variable x, we make the algebra much easier to solve. Continuing with our solution, we do the exact same thing for the predator equation. We set it to 0 and factor out the common variable y. Now we have two factored equations, and for them to be true, either the outside variables or the inside parentheses must be 0. The simplest case is when both x and y are 0. This is our first equilibrium point, known as the extinction state. If there are no rabbits and no foxes, the populations will obviously never change. Now, let us find the more interesting balance point. We set the inside of the prey equation's parentheses to 0 and solve for y, giving us 40 foxes. Then we set the inside of the predator's parentheses to 0 and solve for x, giving us 60 rabbits. This gives us our final answer, the coexistence state. If the park has exactly 60 rabbits and 40 foxes, the number of births perfectly matches the number of deaths, and the populations will stay constant forever. So, we have found where the populations are perfectly balanced. But what if they are not? Let us look at a second example. Imagine a conservationist counts exactly 100 rabbits and 20 foxes. We want to know if the populations are currently growing or shrinking. We plug these exact values into our prey equation. The calculation shows 40 rabbits are born and 20 are eaten, resulting in a net rate of positive 20. Because this is positive, the rabbit population is currently increasing. Next, we evaluate the predators to complete our picture. We substitute the same population numbers into the fox equation. The math shows a growth rate of 10 new foxes and a death rate of 6, giving a net rate of positive 4. This leads to our final conclusion. Both populations are currently on the rise. The abundance of rabbits is providing plenty of food for the foxes to thrive, meaning we are currently in the boom phase of our cycle. This mathematical cycle we just calculated can be visualized beautifully on a graph. What you are looking at is called a phase plane. The horizontal axis represents the prey population, and the vertical axis represents the predators. That dot in the middle is the coexistence equilibrium point we found earlier, where nothing changes. The large loop with arrows shows how the populations actually behave over time, constantly orbiting the equilibrium. As prey increases, predators follow, which then drives prey down, pulling predators down with them, creating an endless loop. Now that we have seen the math in action, it is worth noting why this model is so famous. It was one of the first mathematical tools to prove that nature operates in cycles rather than just settling into a static state. But its power goes far beyond animals in a forest. Economists use these exact same equations to study how high wages act like predators, consuming available jobs. Chemists use them to model oscillating chemical reactions. It is a universal framework for dependent, cyclic behavior. To wrap up our lecture, let us review the most important ideas. The predator-prey model uses two linked differential equations to describe the endless tug-of-war between two species. By analyzing their rates of change, we can find exact equilibrium points where the ecosystem is perfectly balanced. Most importantly, this model proves that even chaotic-looking natural cycles follow strict, predictable mathematical rules. You now have the foundation to understand complex cyclic behaviors across biology, economics, and chemistry. Great job following along.